Hello and welcome back. What I'm going to talk about in this video is the simulation initially of a mass spring damper model that you can see here by this second order transfer function where m is the mass, c is the damping and k is the stiffness. And then I'll move on to the next few slides where I'll talk about the introduction of a discrete time PID controller. So what you'll see here is this transfer function here in phase variable canonical form, where what you can see is I've effectively taken this transfer function, I've divided through by this leading coefficient of m, so therefore I end up with k over m, c over m, and k over m. So then you can see here, in terms of the system gain, is divided by m, this damping term here is divided by m, and this k term here is divided by m. You should remember how to configure this based on the continuous time based on your continuous time studies. And you can see here what I've done is I've put a workspace here for displacement, velocity and acceleration. And you can probably see here how the damping term here relates to velocity and the stiffness here relates to displacement. So, and then you can see here these values are negative as you'd expect. So what I'm initially applying is just a step input. So I'm applying it and then removing it. And for this I've used the signal builder. Okay, I've used the signal builder rather than just the source, well, the step input from the source. And I've done this such that I can effectively remove the step input. So you can see here I've applied the signal for effectively 2 seconds, this input signal. And here you can see the corresponding graphs. So I've used this MATLAB script here to run the graphs. So here you can see I've defined mass, damping, stiffness, the system gain, and then the time which I've defined in the Simulink model. Remember that by default it will be 10 seconds. So I've put t in here within my script to make sure you replace the time in your Simulink model to t. And then I've simulated what the name of the file, so in this case it's model_continuous, and then I've used then the usual graphical outputs here, usual kind of code here for the graphical outputs that you've seen before. And this will give you these graphical outputs given here. So here we've got displacement. So you can see the initial displacement of the system. It's got a little bit of overshoot, so slightly underdamped. And here you can see the corresponding acceleration. So what I'm now going to show you is, so I've taken that continuous system here. So you can see the continuous system here. I've still got displacement, velocity, acceleration. What I've introduced here is negative unity feedback. So negative, because what you're doing is you're introducing, rather than an input, you've got a reference. So this is what we desire. And what I'm doing effectively is to form an error is I'm taking away the reference minus the measured output to form the error. So that forms the error there. So it's negative unity because we're assuming an ideal sensor. So in this case, 1. And here you can see in the feed forward path we've got at the moment a PID controller. And you can see here it's in the Z domain. Okay, MATLAB and Simulink, well, Simulink allows you to effectively, you can get away with, I would say, committing murder. So we're mixing here time domain. So this is in the continuous time domain. This here is in the discrete time domain. But effectively what this is going to do is it's going to capture, because in practice your system is in fact continuous, but because we've got a discrete controller here, it's only going to capture the information at every sample point. And then here I've applied a 0 to hold this block here. So in terms of kind of simulating this and setting up your PID, within the lecture, in the theory, we went through setting up, in terms of the integrator method, we look at the trapezoidal, and in terms of the derivative, or as it's called here, the filter method, we did backward Euler. So what I've done is I've gone in here, you've got to click on this little tab here, and then I've loaded up the trapezoidal and the backward Euler. They're the approximations that I've selected for the integral and derivative. And here you can see sample time, I've selected 0.1 seconds. You'll find the discrete controller block under discrete in MATLAB and Simulink, and as it says here, you need to specify the sampling interval and the discrete model as I've just done so. The 0 to hold, this block here, is located under discrete in Simulink library, and also again if you double click on it as you would do for this discrete time PID and specify the sampling interval. What you now notice, what I've set is the reference, So I've set the reference in this case, because if you look here in terms of what I'm feeding back the displacement. And here, in terms of my reference, it's my desired displacement. So in this case, I've said it's 0.4, so 0.4 meters. And you can see I've applied it for 7 seconds and then removed it. Okay, because I'm removing effectively the reference, I'm using again the signal builder. Just be aware, if I wanted to control maybe the velocity or displacement, what I'd obviously have to do is feed back the corresponding value. So in this case, velocity here and acceleration here, and then my reference would relate to, in the case if I was looking for desired velocity, I'd have desired velocity here, and then I'd be feeding this back. If I had desired acceleration, I'd have it here, and then I'd be feeding back my velocity value. So in terms of, let's go back to the previous slide, this is the code that I've used to simulate this. So what I've done is, because now if you look at the signal builder, the period now, or sorry, the time period that the step input has applied is effectively 7 seconds with an offset of 1 second. I put the offset on just because it's good in terms of visualizing the graphical output, comparing the input with the output. So the offset of 1 second. I've run it for 15 seconds, so we can effectively allow and look at the system to return back to displacement equals 0. And then what I've got is my Simulink model. In this case, I call it model contin and then underscore feedback. And then in terms of the other things, what I've introduced here is a legend, because now what we've got is we've got kind of, in terms of displacement, we've got kind of our reference, and we've also got the output. So that's effectively what we are comparing, because what we desire is the reference, and this is what we get in terms of the output. Okay, so the rest of the lines are the same. And then in terms of tuning the PID controller, so okay, we've set up the type of model we're looking at, and if you click now on controller, what you'll get is PID, PI, PD, P and I. So you can effectively select these. So in this case, I've effectively determined that I need a PD controller in this case, so proportional derivative. However, I would say don't go straight for a PID controller because you might not need all 3 terms. So when you get onto the practical element, just think, computational time. It takes time to kind of make calculations. So to try and minimize that, you might want to just consider exactly what you need. And this table here that you've seen before is quite useful. So in terms of the proportional, you should be aware by now, as you increase the proportional control gain, your system response is going to increase in terms of overshoot. Rise time will decrease, but the overshoot will increase. And you'll get kind of like more oscillation on your response. In terms of a discrete time system, eventually it will come a point where the system becomes unstable. And what will happen is, as a result of increasing the proportional control gain, right, you're going to introduce more overshoot, but what it's going to do is minimize the steady state error. It won't eliminate it, but it will minimize it. So there's a bit of a trade-off in terms of minimizing steady state error, but consequently you introduce kind of more oscillation. The integral, if you introduce an integral, so if you've got steady state error, it might be useful to introduce an integral, because what that'll do is it'll eliminate the steady state error. And then we move on to the derivative. The derivative term is useful if you've got kind of a system that is got quite a lot of overshoot, oscillates quite a bit, because what it'll effectively do is decrease that, and it'll also decrease your settling time. However, it'll have no change on the steady state error. So if you had a system that had maybe no steady state error but had quite a lot of oscillation, maybe you want a PD controller. If it's got very little oscillation but it's got steady state error, maybe you want a PI controller. So in this case I've got a PD, and what I've done here is, if you select PD here and then click apply afterwards, and then what you then do is, within here, what we can do is tune our PID controller. So this within Simulink has got kind of some sort of optimization algorithm behind it that will effectively run, you can run your system, your feedback control system, through various, in this case PD terms, and it'll show you within this window. So if you click on tune here, make sure you click apply, because sometimes if you make changes here and you don't click apply, it'll throw up an error. So make sure you select the options here, click apply, and then move to here. And what you can effectively do is change these 2 tabs. So in terms of response time, to be slower or faster, or transient behavior to be aggressive or more robust. And what will happen is you'll see your original response, and then you'll see your tuned response subject to where you've just changed these two tabs. And you'll notice every time you do that it's changing here in terms of your P, your I, and your D. In this case, you can see I've actually got a full PID when I'm going through this. Okay, so this is not obviously related to the previous one where you just saw a PID. But what you'll see here, you can effectively alter the response time, transient behavior, that sort of thing. What you then do is click Update Block, and then you'll see your controller gain values here. And then if you simulate your sample data control system with that using that MATLAB code, so if I go back up here, this is the MATLAB code used to effectively simulate the feedback control system. What you should notice is that you get a system response that looks like this. So in terms of the reference, you can see the reference being applied for 7 seconds, so from 1 to 8 seconds, and you can see the system output. So in terms of the system response, it reaches the desired value. You've got no oscillation on the response. It looks quite a nice system. No oscillation, and then here you can see the corresponding acceleration plot. And that's pretty much it. So thank you. If you've got any questions, please email me.